still waiting for the boss. Click, click, click.
Time up.
Time up.
So maybe he's not coming?
How does it work here? You start sharp on the time, or you have
Nah.
Every single time.
It's
we
New
start
Zealand.
exactly.
It's not Germany.
Well, I haven't.
But also in Germany you start 10-15 minutes later.
No.
Yeah, no, I've been on the trains. They do not.
Yeah.
There was
The trains, they don't come at all.
these days they don't come at all anymore. There was a time when these clocks were not hardwired, so I took them down to gain more time in lecture, and then and then one year I wanted to do this and it was hardwired, and they are all so yeah, maybe 1 or 2 minutes late.
I have enough slides to fill the whole evening. I don't want to threaten the people.
No soccer team to play today.
Not today. So unlimited time. There's still a lot of
Hello. We were just waiting for you. Did you bring some friends? Yeah, biscuits are there. The hot drinks trolley is excused today because they have this workshop going on. So. May bring this table over.
Why? Where?
Good idea.
For the cookies.
It's more obvious.
I understand.
The best location right here.
We will count. Right, I think we make a start. Anyone that comes later will have to watch the beginning of the recording. I'm just introducing the seminar series 2024 as an opening this year. We will have exciting talks in more of a rhythm of full seminars in PG Talks this year, as well as coupling with the industry people in partnership with the Engineering New Zealand. So that's a little bit of a pilot project that we try in this year. And today we have a guest professor from Germany, and
Yep.
I have asked Kong to introduce the candidate.
Yeah, good afternoon, everyone. So we have a very special guest speaker today, Knut Moller, professor. Oh. So Knut is the full professor at Furtwangen University, Wenningen, Germany, and Knut has been with us for many years. So I think maybe 15 years or 16 years.
No.
So
10 about.
all right. Knut received his master and PhD degrees in computer science and also medical degree. That's surprising. You got a medical degree,
Yeah.
like in human medicine from the University of Bonn. And so Knut and his research has been involved in the fields of machine learning, robotics, and imaging processing. And he became a professor of medical informatics at Furtwangen University in 1998, and he is currently the director of the Institute of Technical Medicine. So he's also a adjunct professor at the University of Canterbury. So without further ado, I think I'll pass the floor to Knut and to start this presentation. Actually, I need to introduce the talk of today is about the EIT, the electrical impedance tomography, the past, present, and future. So this one is a very new technology, especially considered in RCU. So it's kind of a new non-invasive technology to detect perfusion and ventilation. So to provide this real-time monitor things. So it's a very new things, and I think Knut will provide his insights and the basics and the up-to-date research in this field. So we very much look forward to that. Thank
Yeah.
you. Yeah.
Thanks a lot for this introduction. Very impressive. I didn't know that I did all this stuff, but anyway, and you will notice that the technology is not that new. I had the impression that we invented it yesterday, but there are already more than 200 publications that we have published on this topic, and therefore I just have some examples that are brought here, and I'm not going to explain everything that we have done in the last years. And it's just one topic of a lot of topics that we deal with. Since I'm not sure what is your background, the past here in this presentation is more about an introduction. What is electric impedance tomography? What are the basic principles? What are the problems? I will give you some problems at least. Then I will provide some of current work, which is the present. What are the problems that people are trying to solve? And finally, that's the future. We already speculated how long this will be. It will be short. But of course, I'm always open to your fancy ideas, because maybe afterwards you say, oh, wow, these stupid people, they did not look at this and this. It's very easy and clear. And then I'm happy, of course, to capture your ideas as well. Otherwise, I will show you some of what I think is important in the next time to come. First of all, I would like to show to you that New Zealand is nice, but the Black Forest, where we come from, is equally nice, different maybe, but nice as well. And why do I show this? Because I want to make an advertisement, because in September we run a conference there, and of course everybody is invited to submit something and to see us there. Yeah, so that's about in September, nice time in the Black Forest actually, hopefully with some sunshine. And why is this area interesting for us? It's in the southwest of Germany. Here is France, Switzerland, and there's Lake Constance, and these are mountains, the Black Forest area. So, and the HFU has 4 locations actually that are spanning more or less the Black Forest. And why is this interesting? Because the countryside was poor 100 years ago, so people need to invent and work at home, especially in long winter time, when they had nothing to do than just create kids and build some clocks. So there was some industry coming up, a lot of textile industry when the clock industry already went down a little bit, and when textile industries went away, people thought, okay, what can we do? Oh, we are good with needles, so why not build surgical instruments? Yeah, so the region became the main manufacturer in Germany for surgical instruments. And over time, they discovered, oh, well, it's a good business if you have instruments. Yeah, so electrical devices came out of it, and nowadays we are in systems development. For example, in Freiburg now there is a Intuitive Surgical, one of the largest medical robotics companies. So in this environment we are trying to set up some fancy ideas. Yeah? So that's the future of medicine in general. You just have a kind of sarcophage. Yeah? You just put everybody in, and the diagnosis and therapy is done by itself. And these medical people in the future, they just drop some sugar in their coffee and are happy. Yeah? So that's the vision. But of course, we are slightly away from this. At least I think you have enough to do to make it real. I won't be living when this happens to come. But what is important, we need sensors. Sensors that can go and deliver structural and functional information about the patients to determine if something is wrong or not. And how do we know what is right or wrong? Well, we need to have some understanding of pathophysiology. Yeah? So we need some modeling, some understanding of how a body is working. And even now we don't know, just some small parts. So there will be generations of students having enough to do. Yeah? And the next point is we need actuators, how to repair the structures that we find are damaged or the functions that are no longer working. And again, we need to come to individual treatment plans, which means that we need to individualize our models to this patient and then use this information to tailor treatment. So that's the general idea and plan that, or my understanding that I had and developed over the years as a physician and computer scientist, because it matches both quite nicely. Modeling, computer science, complex systems, and how to repair was always interesting for me. So from my background, he already gave some, I would scan quite fast. So I did computer science and human medicine. And in computer science, my PhD was about AI and robotics. So we have developed a robot system that was unfortunately not a surgical one, just relatively simple, catching a ball from no knowledge. We trained it, all the kinematics and dynamics, so that it could reach a ball rolling through its workspace. Yeah, and then when I went into stronger into medicine, we did some work on control of anesthesia. There already the first models were required to describe the dynamics and kinetics of pharmacology. In space medicine, that was for me quite decisive experience, because we were running two projects, and the NASA mission and the Mir mission, which is a Russian mission, and we were investigating the change in the cardiovascular system under microgravity. So over time, the control is disabled. Astronauts that are coming back to Earth, to 2/3 are fainting if you just ask them to stand still. They can't do this. And so the people at NASA wanted to know what happens during this time and what kind of countermeasures can you apply. So what kind of therapy? And there I noticed, well, we had two subjects, and it's quite hard to do statistics with these cases. So that at that time, I understood that physiological modeling is an important tool. So I started to go into this field, and then it was applied to different type of applications, quite wide range. So I don't want to go into it, but ventilation was one of the applications that we were looking at intensively, and electric impedance tomography is one method. So now I'm diving down into the today's topic, where you get some additional information about ventilation distribution in the lungs, which can be used for guiding ventilation. Okay, so I think I'm already late and can skip this. Maybe you are aware that there are different imaging technologies or modalities. Yeah, most people, at least, I think that most of you are from biomed somehow, or engineering, no? So you will know what a CT is and so on. And we will look at electric impedance tomography, where the modality looks at complex electrical resistance of tissue. So that's some additional information that you can get in addition, for example, to computed tomography, where you detect the attenuation of the rays through a body. So different properties are converted into imaging in medical imaging. And the advantage of electric impedance tomography is that it is cheap and does not harm compared to CT or MR imaging or other modalities. I think some of you are looking into optical technology as well. In the DIET project, for example, you look at deformations on surfaces, and I don't have There are some mechanical here in ultrasound. Tissue just has different types of properties, and they all can be used to diagnose the tissue. What is it in a healthy state or not? And tissue resistivities, here you just have a short list. You can see that they vary in a large range, and these differences can be used for imaging as well. And that's the idea of EIT. So there we have, I added here some example. While I talk, you can look at it, because that's the quality of images that EIT is delivering. So it's non-invasive, it's radiation-free. That's what you will see soon. Lung tissue conductivity varies naturally, and that's the advantage. That's why it is applied most often in mechanical ventilation, because inspiration of gas, easily to understand, changes the resistivity in the tissue. Yeah? And though it is not that simple actually, but I'm simplifying it. And yeah, and there are different sources of conductivity changes that you can find. One is from the ventilator or from the drive of the patient himself, and the other one is cardiac activity, so that we have here two images, one with a lower frequency that is shown here, that's the ventilation, and here you can see the pattern of the perfusion where the where it starts in the heart and then goes into the both lung lobes and comes back to the heart. So these are already extracted type of images. This looks maybe a little bit strange, because what can you use this for? So what can you use it for? It's used at the bedside in intensive care units, at least in many hospitals that have those available, because it can show to you ventilation problems during the ventilation process. And so that's more or less state of the art. There are devices that you can buy and you can just apply in a clinical setting. And just an example here, present, this is some of our work already some years ago in cystic fibrosis patients. Maybe, do you know what this is? It's an inherited disease where the mucus is more viscous than normal, and this leads to a higher obstruction of the bronchial tree, because the mucus is not coming out. And usually people were dying in about the age of 25, which increased in the last 50 years up to maybe about an age to 40 to 50, sometimes 60 nowadays, because the treatment is much better. But still, it's an inherited disease. Well, like everybody, we are all dying, but they die early. And what we could show with this technology is which parts of the lung are obstructed. And this is shown here. This is a normal obstruction map of a patient, and this is of a cystic fibrotic person. And why is this of interest at all? I wouldn't care if I'm dying, that maybe here on the right side of the lung I have more obstruction than on the other side, but it's helpful for the treating physiologists or respiratory physiologists and physiotherapists who are treating those people, because they do some kind of manual massage to get the mucus out. So every morning, every day, they have to clear their bronchial pathways. And this could provide feedback for these patients. They could see how productive it is and if certain areas are getting rid of the mucus. And the physiotherapists that we were consulting, they of course said, oh wow, this is great, we can compare and quantify the effect of our methods. Because so far it's all something hand waving. Everybody says my technique is the best because my patients are better. Maybe they live somehow longer, but who knows for what reason. Okay, so these are just some examples. And now how does EIT work? What are the steps that you need to take? Well, first of all, there need to be done some measurement, some chest measurements, and therefore electrodes are attached to the body. There is a current injected and voltage is measured. And from these data, from these measurements, you can create reconstruct so-called raw images. And from these images, then waveforms can be extracted. There can be functional EIT images created showing how much of the tidal volume, the volume that was inhaled, is going to which areas. And last, there can be measures calculated from these, where some of them were developed as well from my group. So in principle, that's the setup, and this is a 10 years old device. Again, so it's not so brand new, but nowadays you have much better electronics and better components, faster and much cheaper, so that devices can be smaller and more powerful. But those are admitted for the clinical practice, and therefore they are used still mainly. Okay. So that's always the same body, showing some. And the principle is quite easy. If you know how CT is working, you will understand easily how this works. So you have an electrode pair where a current is injected, and around the other electrodes around the chest, you measure induced voltages. Like Ohm's law, there is a relation between voltage, the resistance, and the current, right? And this is similar, at least in intuition. And now what is done, you just switch to the next pair of electrodes, and again you just measure the voltages, and this is done around the whole chest, and this leads to in total 13 frames, 13 measurements all the time, 16 times, and this makes up 208 measurements per image that you have available. So the principle is relatively simple. If you have some impedance here, some increased impedance, then that's the back projection method that is applied in CT as well, by overlapping all those. Come on. I was speeding it up a little bit too much. So then at the end you have such a dot somewhere which shows, oh, there is something different, which looks easy and simple. Unfortunately, it's not so simple as CT reconstruction. Why? Do you have some idea? Well, CT rays, they go straight through, right? So that's a simple linear overlapping. You just need to add those up and then you're done. This is somehow different with electric currents. You all know that they just take the shortest path. So somewhere, which makes it a little bit more complicated. We need some finite element mesh and thorax. So those are discretizations of a lot of discrete conductances, resistance here, and they describe the relation between the resistance in one position and the voltage measurements that are made at the electrode positions. So, and this allows now arbitrary paths through the system. So there need to be one thing in addition. need to be understood. At the present systems, they all use TD, so-called temporal difference EIT, because temporal differences or differences mean that certain constant factors are just cancelling out. Yeah. For example, what is unknown most of the time is the resistance of the electrode and the skin contact. It's very difficult to measure and determine those. But if you have just two measurements in a row and you subtract them, then this part is just cancelled. You don't need to identify. It just needs to be good enough to deliver information at all. So that's the principle of difference images, and it's shown here. So you have at different time points, you have images, and if there is something changing in between, you are able to detect what has changed. But you need, of course, a changing system. And this is exactly true for mechanical ventilation, because the gas is going in and out. So you have constantly changing impedances in the lung. That makes it very nice, feasible for this temporal difference imaging. In absolute images, that's this case here, you can apply this always, not just in situations where you have changing impedances, but usually it does not work. That's the problem. So it's nice to write, it's always applicable, but it does not work in current settings. This is not always applicable, but it works. And with some tricks, you can often use such systems even under static conditions. That's what at least came to my mind recently. Okay, so the principle, I won't stay long on this part here. It's an optimization problem. That's all what you should know. So that's this argmin up there. So you have the forward model, which is your finite element model. It maps the changes in the impedances to the induced voltage changes at the outside, and of course then it's a minimization with the measurements. So you try to adjust the impedances such that you reconstruct the measurements. That's a typical least square formulation. And now if you linearize the problem, you create a Jacobian so that the changes, so that it maps how changes are influencing the voltage changes, then you get a linearized problem which can be solved very fast in the usual way, here looking at the Moore-Penrose inverse. Unfortunately, this matrix is ill-conditioned, so we need regularization. That means some additional knowledge is to be added so that you can solve this, that it gets a unique solution. Otherwise, because you just have 208 measurements, but usually thousands of parameters in this finite element map, you have multiple solutions. That's typical ill-posed problem. So in general, what do you do? So for every element, you know how changes in this element are influencing the voltages outside, and this leads to some These are actually 208 values for all the measurements, how they are influencing. Changes in this position are influencing the voltage measurements, and you do this in all the others in the mesh, and then this is just a linear combination, and then you get some output, and if you visualize, then if you do the matching with the measurements, then you get some values. These are always the impedances in these local regions according to these optimization process, and you are almost done. The problem is that there are multiple ones, multiple solutions, if you don't apply the regularization correctly, and you don't know which one to choose, and that's then the task of this regularization process. Wait a second, no, that's not this. This one here. So, and it can be prettified, and this is what you see on the devices. So actually it is just a resolution of 32 by 32, and with some filtering it looks a little bit nicer. Okay, what can be done with this? A typical application for those who are familiar with mechanical ventilation is an attempt to find the best PEEP setting or optimal PEEP setting, being a compromise between hyperdistension and collapse. For those who are familiar with ventilation, they know that pressure always in some regions leads to so-called hyperdistension, and other areas may be collapsed, so there is the pressure not high enough to open up the lung. And what you would like to have, of course, is that both are vanishing, so you are choosing a certain minimum here than for the PEEP setting. So that was quite useful. This is all state of the art at the moment, and now I will show you some of the present. I'm not going through all this stuff, and I'm not going through the mathematical background of the fast optimization. I have always placed some small references in case that somebody is interested to see those. But what I would like to point out is that even with temporal difference imaging, there are still some problems with these EIT in ventilation monitoring, and we have quite some equipment for this. So we use so-called body plethysmograph, the EIT device, and motion tracking at the same time to do some evaluations, or did some evaluations. I'm not going through this, so we could distinguish where breathing is going. But what I want to show to you is a simple problem that everybody may come up with, because you have just a belt around one layer. You have one layer here, and what happens during ventilation? Well, the problem is the lung is moving. So you have actually in your ventilation path not the same area, sometimes filled, sometimes not filled. So there is some blurring in those images, and we could at least nicely show that there is that the layer is important where you place it, and of course that you have quite constant effects showing nicely that this is and in which range you can expect problems to occur. So these are always the ratio that we were using of delta I to delta V. So the impedance differences that were induced compared to the volume that was inflated into those lungs. And they change because you have different area of a different amount of lung volume under the recording plane. Okay, so that's quite for these upper ones, and of course it's even more apparent in the lower belts, because there the diaphragm can come in the expiration and has no relation to lung tissue at all. Yeah, so this is horizontal movement, but in addition you have vertical motion as well. Yeah, so the thorax is expanding, which leads to different positions of the electrodes in your calculations. And even this can be compensated, and you can do some work on it to improve it. So the artifacts that you can see here can be dramatically reduced with some compensation mechanism. And actually it was quite nice to see that it even works the other way around by minimizing these artifact measure. You could find the thorax excursion. There was a nice clear minimum in the data that we could find. Okay, just to give you some ideas how simple it is to produce publications in this area. You just make some measurements and then some compensation, and you have some nice curves, and next one and next one. So it's a good field because can be applied by almost everybody with students, so nothing harming, and has a lot of potential. Maybe. Okay, so I don't want to go into this here. Let's check what. Then. So, for example, what else can be done? You can incorporate prior knowledge. Yeah, this is nothing special to EIT. I would like to emphasize that's in medicine everywhere. Every sensor signal that you have has some prior knowledge in its evaluation. It's just by converting it into the measurement that you want to have. Yeah? Usually there are some electrical quantities, but they are converted either into meter or pressure or whatever. And this is already some prior knowledge that is going into the system. And the same applies in EIT. There we can use thorax geometry, for example, to simplify this. So structure can be used, and actually we have used this even to set up some 3D imaging where you can overlay structure from a CT with the ventilation, the functional data coming from EIT. So that's already quite nicer to look at than the first blurred images that I have shown to you. But it's all fake in some way because there's prior knowledge in it. And the prior knowledge shapes more or less this. I could make it look like a bunny as well, or something else. That's prior knowledge that is placed in there. But it looks nice, and for medicine, for physicians, it's easier to interpret. And the data, I think, is still the same. So the information is not incorrect. But nobody would expect, of course, a bunny on his intensive care unit, certainly. But that's like with AI. There you can make everything happen as well. It's just a matter of how you design your system. And actually, those are typical ill-posed problems as well. You have a lot of parameters, and depending on the order of the data that you put in, you will get other results. But nobody cares, as long as on average it's just looking fine. Which is okay in many applications, not in all. I'm not sure that I would like to get into a plane that is controlled by AI, to be honest. Or live next to a nuclear plant. I think engineering, solid engineering is sometimes better. Okay, what else? Maybe I'm too. Should speed up a little bit. So maybe I should skip. We have done a number of work how to include prior knowledge. This can come from contour information and anatomical structures. It could be as well coming from physiological models about the dynamics, which was not yet done. So temporal aspects are not considered in current EIT imaging, so that's already a little bit of future. And there have been quite some work in clustering, some AI methods, spectrograph wavelets, or and DCT, that's a discrete cosine transform. So you can use certain transforms to reduce the number of degrees of freedom, so to scale the behavior of your optimization task. But I'm not going into this. I think I should skip because it's too long already. I want to show to you a short just idea again about pulsatile signals. So there are a number of methods how you can extract from the EIT images the components coming from the blood flow. Yeah? So more or less, and from the heart. There's a phase difference here between heart action and perfusion through the lungs. Clear, because it's first pumping and then the blood is going there and then it's coming back. You could see this, I think, quite nicely in the video at the beginning. And then, of course, there are standard techniques. One here, harmonic analysis, is work from Alberto, who's sitting here and has some potential as well. And what we do at the moment, actually, we try to separate the data in the raw setting already, not to first reconstruct an image and separate them, but to separate them first and then reconstruct images from perfusion data and from ventilation data. Why? Because then you have less artifacts in the system and you can use different prior knowledge for this reconstruction process. Okay, so usually what can be done here as well, you can use saline bolus, because if you put saline, that's a contrast media and you get nicer images. But that's not so important at the moment. What I wanted to show to you, what is the potential. So we did some experiments with normal breathing subjects, and they had to hold breath on different volume levels. Very simple experiment. Everybody can imagine. You and then and you stop for some time, and this with EIT monitoring. And what did we find? I just, this is, so in these breath holds, wasn't, should be, here it is. Yeah. So these are normal breaths, these are normal breathing cycles, and here are the breath holds. And you can see, maybe it's, I don't know, from the back, maybe not, you can see that there is some variation. This is the heartbeat or the perfusion. Then again, there's some ventilation, and on a different level, you have again the breath hold. And if you look at it, you can see, wow, the amplitudes are changing, right? So the content, the filling of the lung has some influence on the perfusion. And we looked then even at the forms, the shapes of these. And if you look at them, you can see a systematic change even in the perfusion waveforms. So there are quite details that you can extract from those. So in total, this is how it looks like on different lung filling levels. So, but why is this the case? Unfortunately, I can't give you the answer. I would like to know as well. Because what we saw in ventilation is something similar. If you look at the mouthpiece on the cardiac oscillations, you see changes in the waveform as well. But one is measured directly from the blood flow, and the other one is a transformation through the bronchial tree of the mechanical stimulation through the heart. So, yeah, as I said already, there are lots of problems that are left. So now I'm at this summary, maybe still okay. I can skip those as well relatively fast. So what is important, we have a look in this technique, a low signal to noise ratio. That's why we have these blurred images. It's an ill-posed problem, so you need some criteria to determine what is your truth. Yeah, so what do you want to extract from the data? Then there are different forms of priors that can be incorporated. I didn't talk about it. There were quite a number of papers as well. If you want of general constraints, patient-specific data, there can be some Bayesian embedding, so you can think of things in a probabilistic setting. Priors, yeah, that's not a problem. Priors are sometimes wrong. And then you get even worse than before without those priors. So you need to detect somehow what, if they are still reasonable, let's call it that way. So there is quite some work on this. Then there is quite what I mentioned already. I think this is an important aspect as well, because the lung is not changing from one time to the other dramatically. So one breathing to the next should be related to each other. Yeah? Because in these ill-posed problems, it could even jump from one solution to another one. And then they are no longer comparable. Yeah? This is if you have, if your regularization is too weak, this can happen. And temporal priors may already add some expectations into your reconstruction. And as well, this could be a good path to introduce physiological modeling into the EIT reconstruction. Because you know from your models what should be the development. So for example, if you increase the PEEP, you should know what the are the, at least the tendency in your next breath. Yeah, and yeah, validity checks are important. Yeah, 3D reconstruction is still an issue. We did some of this. You can use multi-frequency EIT or even temporal, how do you call it? You can use different frequency as a frequency difference method as well. You can obtain EIT images with different frequencies, because impedances are frequency dependent, as you know, and then you can use as well differences in these frequencies or in the frequency behavior of certain tissue to create an image. Absolute EIT is still work and would be helpful if somebody solves it finally. And what is another nice application is that you can estimate lung blood pressure in the lung circuit by capturing perfusion velocity or pulse transit time via EIT. So that would be a clinically very relevant application. Then there are other options and developments that would be nice, contact-free EIT. So if you don't need to have electrodes attached to it, there are some capacitive or electromagnetic coupling options, but usually it increases the noise even, that is already bad. Nevertheless, if somebody finds a clever solution, would be nice. You could combine image modalities, for example, PET EIT. You know maybe in a normal, usual standard imaging, that's what is done, PET CT, or you can combine even MRI EIT if you have just electrodes that are not magnetic. Another option would be, instead of using TD EIT, in static cases, you could try to induce differences in your domain, for example, by moving them. And then you could again use TD EIT to discover certain parts within. And then Jeff always comes up with a multipath problem, which requires, I think, much higher resolution in the voltage measurements than what we have at the moment, but can be thought about. So I would be happy to get now your suggestions, of course, what we should do in the next few years, and then we write all of your names, of course, on the papers. Yeah, so okay, yeah. Maybe the last slide I forgot. So still a long way to go, at least. Yeah.
Do you have time for some questions?
There are no ridiculous questions. I'm always afraid if you say it's a ridiculous question.
Anyone put an electrode down the esophagus?
What? Electrode down in the esophagus? There have been some, but for phrenic nerve stimulation and measurements. But even EIT with inside electrodes was done. I think even in the thorax, people have placed some inside.
And the bronchial tube?
Mm.
That's not so much a result.
Yeah.
Yeah, the closer you get, the better, of course. But it's no longer non-invasive. And that's a very important property, especially if you have students to subjects.
I have a. Oh yeah, go ahead.
Okay. Can you just describe the multi-part problem a bit more, if you know anything about it?
I know somebody who can describe it, maybe. Well, maybe I go back to the. Wait a second. Do you remember these FEMs?
Yeah.
So if you're inserting a current in one location, these currents go everywhere. And now the question is, which of those paths is influential for your voltage measurements? Actually, it's an overlap. But can you get additional information from these different paths? If you could distinguish them, or if you could find out what is the straight one going through. And does this simplify the problem? At the moment we don't care, it's more a steady state. Okay, here you have your current that is injected and then the induced voltages. They're just summarizing all the effects in there. There is no distinguishing between multiple paths in there. At least it's not used. And yeah, we don't distinguish those.
How do you get the beginner's question? How do you get the elongated pictures if you only have one belt in one layer?
Yeah, of course we did multiple belt measurements. Sorry. Yeah, I didn't.
Okay.
I can show.
Scans.
Yeah.
And then
We
you put
have.
that picture together.
Yeah. I can show even a video how this looks like if you.
Yeah, I
assemble this.
was just thinking like you have these along the axis also just by one measurement around one circumference.
Yeah. Of course, the differences you can clearly see. What happens between inspiration and expiration. This is with one layer already, but we did multiple layers there, so that we could find out how does it vary with the layer that you are using. And of course
that you had like on the second to last slide or something.
vertical shift. Wait a second, is 40.
No. The
No?
last second to last slide.
The second to last. Okay. That was somewhere here.
Just we go before.
No.
Where you had those images of like front. Yeah, this one.
This
So
one.
how
Okay.
do you get this
Okay.
image from one?
Yeah. Okay. Yeah. So these are actually in simulations created.
Okay. Next question.
It was demonstrating that this works.
Okay.
But again, what you do is you can even, with one belt, you can still get 3D information because the current is not limited to the plane. It's
How
even
much-
going
how much you
up
would
and
get?
down.
How much would you get?
that's again a matter of prior knowledge. Here we can, if you have the structure, the 3D structure from CT, and you map your inductances into the system, you can create it from this.
Sure.
Yeah? But the question is still, what is real? You know, what is the real truth? What is the ground truth? Yeah? Because we don't know. What we measure is somehow fit here, and we have certain assumptions how it is distributed. It's a kind of cone up and down that you're assuming in the influence, and you use the structure from the CT.
But you actually have answered my question because it's about the prior knowledge. You actually already assume the shape or ventilation area for your
Yes.
optimization problem.
Yeah, that's
so you can't need the CT image first, or like at
you
least
need the CT first,
Yeah.
individual CT. And of course, there's always the question, if the CT is 2 weeks old or 2 months, what is the value of this?
Yeah. So the patient, when they came into,
It's-
I don't know, like ICU, like they need to first take a CT image first, and then
Well, it's
get
just
structure.
it's just done if the CT is taken anyway. Yeah? So for ethical considerations, you don't take a CT to do an EIT measurement.
Well, I will close the official part here. There are biscuits for like individual conversation and mingling afterwards. Let's thank the speaker again. Thank you. We'll be in touch for the next seminar.
Yeah. So, for example, there was a student who devised.
Much further progress in the EIT machine.
No, not yet. In these 2 days I was working on something else, trying to always jumping from one thing to the other.
Yeah, yeah, that was the same. Yeah, I should be working another job. Sounds interesting.
So, well, actually, I have
Yeah, there's actually a lot of just point of development. One is the hardware,
Yeah. Different priors and whatnot. For my system, it's quite easy in terms of priors because you know, I know the mechanical system, but the prior is maybe like what you're expecting to sense.
No, the prior is a relation. So, for example, you
Yeah. Or the minimum required kind of edge you need to detect. The multi-path problem is interesting though. Essentially, you look at phase shift between the signals because you'll be getting
students are spending so much time with the subject. We can solve any of the problems. We can do everything. Gave him some problems and then
Yes. But you see the response. That's only if the students respond to that.
That's why it is difficult.
Well, like in a
Did you get your picture?
I have many.
Because I was about to say, but I said like, no, this is recorded. You shut up. It's like, do we still need to wait for the acknowledgement slides?
I placed everything because I saw his face and
I took that one also, so
Because I was like, we can't just stop here. Where's the acknowledgement slide?
wait a minute. I mean, I should have taken a picture of those all those who are involved somehow, which is done. But anyway, yes, sure. This is what maybe and I will.
from what we should you have
should I set up some slides?
You get different responses with
I mean,
so it's like
So one part of the wave goes through,
You
and
will
the other one
represent the
and
you guys will be
this interface is moving,
representing the
property
DCPM project.
of the wave shifting back.
You were
Do I have
in
to
Germany.
write down both?
No, one and a half.
What is it?
Yeah, you took me to the thing, and then nobody had told me what even the acronym was, and I was like, yeah, totally understand what's happening.
My goodness!
Jeff told me
You
afterwards.
were.
Which slide do you want to have?
I mean, you participated in the
Yeah,
DCPM.
Yeah,
What
a
was it?
great time.
Midterm meeting. I mean,
Yeah, I know.
Nice game.
yeah.
One enough. One is one is enough.
I've looked at
What is moving and what is not moving.
yeah.
Which one do you
Yeah,
want?
that's I've looked
I mean,
into
see which
No,
one
not
comes out.
like going.
You
I'm
should
sorry.
be in the middle.
Are you in the picture?
Yes, the middle. Yes, you are.
I'll just stand behind you and then put the hair.
You are
And the only one knows
Maybe I should show you the photo of mine.
No, that's not gonna work
Because it
because
was
like
this,
the
because of the
projectors.
reduction on your. We can stand
No,
like
they want
this.
the
Then you
slides.
stand like this.
Yeah.
Alright.
Alright, I mean, this is
Maybe we
good.
can go a little bit to the side. No?
Just squint a little bit.
Oh, I'd have to do the Tippy Toe thing, but then.
Well, why don't you turn
We need to
turn
be on
off
the
one?
point where it's darker.
One monitor, like turn off one.
Yeah, but then you don't have an image. That's
Well,
Yeah, but then we
No,
just
no.
need to come a bit
Oh,
off.
we'll go behind the desk.
how we can go.
Yeah.
Yeah,
That'll do.
that's
That'll do.
good. That's good. Behind the desk is
Oh, then
much
you have
better.
this
Oh yeah.
this screen thingy.
We can just turn off one
Jamie,
of
what
them.
is?
How many people do you need in the picture?
It will go to the website of the DCP.
Okay.
Smile.
So
Mine, you're
no
there.
worries, nobody will see it.
You can zoom in.
No, I think there's Germany,
Do
Hungary,
you
New
want to do
Zealand,
the
Russia,
front
Jeff,
slide again?
all the
First
others.
slide?
Yeah.
So acknowledgement.
Jamie just gets to eat biscuits. This is
Acknowledgement.
unfair.
Or the front one and the acknowledgement one. So maybe we
I
choose
got to
which
do
one.
this now. Oh, nobody can see. I can be tall.
See.
See if
Do you
No, we
want to
can-
have the last one?
The last one. We have one more.
Oh, we want more.
I did that in all Jeff's phone.
Yes, this one.
Oh, this
I was
one.
like,
Yeah,
This
this
one.
one.
This
He
one.
needs the
Oh,
acknowledgement.
That's the.
This is the sponsor one.
I'll be
Where's
honest.
the German flag?
Sponsoring. DCPM should be
Yeah, it's a very
visible.
skinny
really
German.
sad.
flag, yeah.
No, it's not. It's too far down.
Oh.
But it's on,
Alright.
you're taking that side, no?
Where's the German flag?
Yeah,
In
it's the
Jeep's
federal
office.
minister.
Yeah, yeah.
I know everyone knows.
And the DCPM is visible.
Yeah, it's
Where's
next,
the DC?
next to the.
It's down there.
Well, let me zoom in.
I can make it bold,
Good. Okay.
bigger.
Perfect.
Have a look.
Perfect.
Wait, you
Yeah, I
probably
played around
have, you
with
have to highlight it or
electrical
circle it
impedance.
in.
Oh,
ET, it's like time domain
Is it good?
reflectometry.
You will find some way.
Similar principles, but you've got like a wave guide for it.
Do I look tall?
Because you look at the
Of course, you are
That's the
tall.
other.
Yes, you're tall, but you're not.
You can look at it
not
from
looking to the
distance,
camera.
but-
You're looking left to right.
If you
Wow,
just
they
get a
sound
long,
cool.
It doesn't matter.
I just tried it with a long coax cable and you put a pulse.
Perfect. Thank you very much.
No worries, thank you.
And then that will reflect at the end of the cable and come back down. And then if you deform the cable in certain places,
Anyone
you've got
biscuits?
different
impedance, they are.
yeah, but it's not as soon as you have a cable that doesn't have
already
a
tried
good
the other one.
characteristic
I was there.
you don't know where exactly it becomes a very noisy signal because there's a lot of energy being absorbed every time there's an impedance.
Yeah, so then you get out
You have budget for other things that we don't.
every millimeter is giving a little bit of effect scattering.
I would
And
be
then
advised
you
to
get
get
a
the same one
clean
because
signal.
it's again old like model things. I guess somehow they might have a different. Actually, we need to turn off the light. Where's the light?
They might just be on the auto timeless. I think most of them are.